In computer science, the time complexity of an algorithm quantifies the amount of time taken by an algorithm to run as a function of the length of the string representing the input. The time complexity of an algorithm is commonly expressed using big O notation, which excludes coefficients and lower-order terms. When expressed this way, the time complexity is said to be described asymptotically, i.e., as the input size goes to infinity. For example, if the time required by an algorithm on all inputs of size n is at most 5n3 plus 3n for any n, the asymptotic time complexity is O. Time complexity is commonly estimated by counting the number of elementary operations performed by the algorithm, where an elementary operation takes a fixed amount of time to perform. Thus, the amount of time taken and the number of elementary operations performed by the algorithm differ by at most a constant factor. Since an algorithm's performance time may vary with different inputs of the same size, one commonly uses the worst-case time complexity of an algorithm, denoted as T, which is defined as the maximum amount of time taken on any input of size n. Less common, and usually specified explicitly, is the measure of average case complexity. Time complexities are classified by the nature of the function t. For instance, an algorithm with t equals O is called a linear time algorithm, and an algorithm with t equals O and mn equals O for some mn greater than 1 is said to be an exponential time algorithm. Table of common time complexities. The following table summarizes some classes of commonly encountered time complexities. In the table, poly equals XO, i.e., polynomial in X. Constant time. An algorithm is said to be constant time if the value of t is bounded by a value that does not depend on the size of the input. For example, accessing any single element in an array takes constant time as only one operation has to be performed to locate it. However, finding the minimal value in an unordered array is not a constant time operation, as a scan over each element in the array is needed in order to determine the minimal value. Hence it is a linear time operation, taking O time. If the number of elements is known in advance and does not change, however, such an algorithm can still be said to run in constant time. Despite the name of constant time, the running time does not have to be independent of the problem size, but an upper bound for the running time has to be bounded independently of the problem size. For example, the task exchange the values of A and B if necessary so that a B is called constant time even though the time may depend on whether or not it is already true that a B. However, there is some constant t such that the time required is always at most t. Here are some examples of code fragments that run in constant time. Int index equals 5, int item equals list index, if then perform some operation that runs in constant time, else perform some other operation that runs in constant time. For I equals 1 to 100, for j equals 1 to 200, perform some operation that runs in constant time if t is O. This is equivalent to and stated in standard notation as t being O. Logarithmic time. An algorithm is said to take logarithmic time if t equals O. Due to the use of the binary numeral system by computers, the logarithm is frequently base 2. However, by the change of base for logarithms, log n and logbn differ only by a constant multiplier, which in big O notation is discarded. Thus O is the standard notation for logarithmic time algorithms regardless of the base of the logarithm. Algorithms taking logarithmic time are commonly found in operations on binary trees or when using binary search. An O algorithm is considered highly efficient, as the operations per instance required to complete decrease with each instance. A very simple example of this type is an algorithm that cuts a string in half, then cuts the right half in half, and so on. It will take O time since we chop the string in half before each print. This means, in order to increase the number of prints, we have to double the length of the string. function to recursively print the right half of a string var right equals function, var length equals street length, helper function var help equals function. Recursive case. Print right half if prints characters from index until the end of the array console.log. Recursive call. Call help on right half help 2. Base case. Do nothing. Help polylogarithmic time. An algorithm is said to run in polylogarithmic time if d equals OK for some constant k. For example, matrix chain ordering can be solved in polylogarithmic time on a parallel random access machine. Sublinear time. An algorithm is said to run in sublinear time if t equals O. In particular, this includes algorithms with the time complexities defined above, as well as others such as the O-Grover's search algorithm. Typical algorithms that are exact and yet run in sublinear time use parallel processing, non-classical processing, or alternatively have guaranteed assumptions on the input structure. However, formal languages such as the set of all strings that have a 1 bit in the position indicated by the first log bits of the string may depend on every bit of the input and yet be computable in sublinear time. The specific term sublinear time algorithm is usually reserved to algorithms that are unlike the above in that they are run over classical serial machine models and are not allowed prior assumptions on the input. They are however allowed to be randomized, and indeed must be randomized for all but the most trivial of tasks. As such, an algorithm must provide an answer without reading the entire input. Its particulars heavily depend on the access allowed to the input. Usually for an input that is represented as a binary string b1, bk, it is assumed that the algorithm can in time request and obtain the value of bi for any I. Sublinear time algorithms are typically randomized, and provide only approximate solutions. In fact, the property of a binary string having only zeros can be easily proved not to be decidable by a sublinear time algorithm. Sublinear time algorithms arise naturally in the investigation of property testing. Linear time. An algorithm is said to take linear time, or O time, if its time complexity is O. Informally, this means that for large enough input sizes the running time increases linearly with the size of the input. For example, a procedure that adds up all elements of a list requires time proportional to the length of the list. This description is slightly inaccurate, since the running time can significantly deviate from a precise proportionality, especially for small values of n. Linear time is often viewed as a desirable attribute for an algorithm. Much research has been invested into creating algorithms exhibiting linear time or better. This research includes both software and hardware methods. In the case of hardware, some algorithms which, mathematically speaking, can never achieve linear time with standard computation models are able to run in linear time. There are several hardware technologies which exploit parallelism to provide this. An example is content addressable memory. This concept of linear time is used in string matching algorithms such as the Boyer-Moore algorithm and Uckanon's algorithm. Quasi-linear time. An algorithm is said to run in quasi-linear time if d equals O for any constant k. Linear arithmetic time is the case k equals 1. Using soft O notation, these algorithms are O. Quasi-linear time algorithms are also O for every epsilon greater than 0, and thus run faster than any polynomial in n with exponent strictly greater than 1. Algorithms which run in quasi-linear time, in addition to the linear arithmetic algorithms listed above, include in-place merge sort. Quicksort, O, in its randomized version, has a running time that is linear arithmetic in expectation on the worst-case input. Its non-randomized version has a linear arithmetic running time only when considering average case complexity. Heap sort, O, merge sort, intrasort, binary tree sort, smooth sort, patient sorting, etc. In the worst case, fast Fourier transforms. Mongeray calculation. Linear arithmetic time. Linear arithmetic time is a special case of quasi-linear time where the exponent k equals 1 on the logarithmic term. A linear arithmetic function is a function of the form n log n. An algorithm is said to run in linear arithmetic time if t equals 0. Thus, a linear arithmetic term grows faster than a linear term but slower than any polynomial in n with exponent strictly greater than 1. In many cases, the n log n running time is simply the result of performing a theta operation n times. For example, binary tree sort creates a binary tree by inserting each element of the n-sized array one by one. Since the insert operation on a self-balancing binary search tree takes O time, the entire algorithm takes linear arithmetic time. Comparison sorts require at least linear arithmetic number of comparisons in the worst case because log equals theta, by Stirling's approximation. They also frequently arise from the recurrence relation t equals 2t plus O. Subquadratic time. An algorithm is said to be subquadratic time if t equals O. For example, simple, comparison-based sorting algorithms are quadratic, but more advanced algorithms can be found that are subquadratic. No general-purpose sorts run in linear time, but the change from quadratic to subquadratic is of great practical importance. Polynomial time. An algorithm is said to be of polynomial time if its running time is upper bounded by a polynomial expression in the size of the input for the algorithm, i.e., t equals O for some constant k. Problems for which a deterministic polynomial time algorithm exists belong to the complexity class P, which is central in the field of computational complexity theory. Cobham's thesis states that polynomial time is a synonym for tractable, feasible, efficient, or fast. Some examples of polynomial time algorithms. The quicksort sorting algorithm on n integers performs at most operations for some constant a. Thus it runs in time and is a polynomial time algorithm. All the basic arithmetic operations can be done in polynomial time. Maximum matchings in graphs can be found in polynomial time. Strongly and weakly polynomial time in some contexts, especially in optimization. One differentiates between strongly polynomial time and weakly polynomial time algorithms. These two concepts are only relevant if the inputs to the algorithms consist of integers. Strongly polynomial time is defined in the arithmetic model of computation. In this model of computation, the basic arithmetic operations take a unit time step to perform, regardless of the sizes of the operands. The algorithm runs in strongly polynomial time if the number of operations in the arithmetic model of computation is bounded by a polynomial in the number of integers in the input instance, and the space used by the algorithm is bounded by a polynomial in the size of the input. Any algorithm with these two properties can be converted to a polynomial time algorithm by replacing the arithmetic operations by suitable algorithms for performing the arithmetic operations on a Turing machine. If the second of the above requirement is not met, then this is not true anymore. Given the integer, it is possible to compute with n multiplications using repeated squaring. However, the space used to represent is proportional to, and thus exponential rather than polynomial in the space used to represent the input. Hence, it is not possible to carry out this computation in polynomial time on a Turing machine, but it is possible to compute it by polynomially many arithmetic operations. Conversely, there are algorithms which run in a number of Turing machine steps bounded by a polynomial in the length of binary encoded input, but do not take a number of arithmetic operations bounded by a polynomial in the number of input numbers. The Euclidean algorithm for computing the greatest common divisor of two integers is one example. Given two integers and the running time of the algorithm is bounded by Turing machine steps, This is polynomial in the size of a binary representation of n, as the size of such a representation is roughly. At the same time, the number of arithmetic operations cannot be bound by the number of integers in the input. Due to the latter observation, the algorithm does not run in strongly polynomial time. Its real running time depends on the magnitudes of n and not only on the number of integers in the input. An algorithm which runs in polynomial time but which is not strongly polynomial is said to run in weakly polynomial time. A well-known example of a problem for which a weakly polynomial time algorithm is known, but is not known to admit a strongly polynomial time algorithm, is linear programming. Weakly polynomial time should not be confused with pseudo-polynomial time. Complexity classes. The concept of polynomial time leads to several complexity classes in computational complexity theory. Some important classes defined using polynomial time are the following. P. The complexity class of decision problems that can be solved on a deterministic Turing machine in polynomial time. NP. The complexity class of decision problems that can be solved on a non-deterministic Turing machine in polynomial time. ZPP. The complexity class of decision problems that can be solved with zero error on a probabilistic Turing machine in polynomial time. RP. The complexity class of decision problems that can be solved with one-sided error on a probabilistic Turing machine in polynomial time. BPP. The complexity class of decision problems that can be solved with two-sided error on a probabilistic Turing machine in polynomial time. BQP. The complexity class of decision problems that can be solved with two-sided error on a quantum Turing machine in polynomial time. P is the smallest time complexity class on a deterministic machine which is robust in terms of machine model changes. Any given abstract machine will have a complexity class corresponding to the problems which can be solved in polynomial time on that machine. Superpolynomial time. An algorithm is said to take superpolynomial time if t is not bounded above by any polynomial. It is omega time for all constants c, where n is the input parameter, typically the number of bits in the input. For example, an algorithm that runs for 2n steps on an input of size n requires superpolynomial time. An algorithm that uses exponential resources is clearly superpolynomial, but some algorithms are only very weakly superpolynomial. For example, the Adleman-Pomerantz-Rumley primality test runs for no time on n-bit inputs. This grows faster than any polynomial for large enough n. But the input size must become impractically large before it cannot be dominated by a polynomial with small degree. An algorithm that requires superpolynomial time lies outside the complexity class P. Cobham's thesis posits that these algorithms are impractical, and in many cases they are. Since the P versus NP problem is unresolved, no algorithm for an NP-complete problem is currently known to run in polynomial time.